Question 3, we've got a particle on a plane, a rough inclined plane, and we're given some facts about the coefficient of friction and indeed the angle of the plane. And in part A, we've been asked to find, in terms of m and g, the magnitude of the normal reaction force of the plane on P. So as usual, let me add all the forces in. Okay, there are the forces involved, and we have to find R. To find R, it's best to resolve perpendicular to the plane because in that way we can eliminate or not include F. So effectively I'm resolving in the direction of R. So R, which is the only force pointing away from the plane, must be equal to mg, but we have to turn mg through the angle of alpha. So mg will be multiplied by cos alpha. Now, to find alpha, we use the fact that tan alpha is equal to 5/12. So there's a right-angled triangle, the opposite being 5, the adjacent 12, and this value you should know to be 13. So if I want cos alpha, this is the adjacent over the hypotenuse. So if I substitute that into my value for R, so therefore I get that R is equal to 12 mg divided by 13. And I'm going to leave it like that because it's going to be easier to take that further down into the question rather than calculating g into it as 9.8. And part B, we've got to show that as P slides down the plane, the acceleration of P down the plane is equal to this. So at least we know what we've got to aim at. So to form an equation of the acceleration down the plane, we have to apply F equals ma. And I tend to apply F equals ma in the direction of the acceleration, which is down the plane. So it's parallel to the plane. So I'm resolving parallel to the plane. Okay, forces pulling in the direction of A will be a proportion of mg. Again, we have to turn mg so that it is pointing in the direction of parallel to the plane, and we turn it through 90 minus alpha. So mg will have to be multiplied by sine alpha. So F equals ma. The pulling force, mg, sine alpha, minus the friction, must be equal to the mass, which is m, multiplied by a that we want. And as we're accelerating down the plane, the friction has reached the maximum, and that maximum is equal to mu r. So I can substitute F is equal to mu r. I can also substitute sine alpha using my triangle here. So I get mg. Sine alpha is the opposite over the hypotenuse, so this is 5/13, minus mu r is equal to ma. R we've already worked out as this value, so I can substitute that in as well. So I get this. The m's will cancel all the way through. Now we want A to be the subject, and I can take a factor of g/13 out of the left-hand side. So A is equal to g/13, and this is 5 minus 12 mu. And that's the answer they wanted. Now, for just one mark in part C, we've been asked to state what would happen to P if it's released from rest, but mu is greater than or equal to 5/12. Well, let's sub mu is equal to 5/12 into our equation above for the acceleration. Mu 5/12, the 12 cancel, 5 minus 5 is 0. So A would be 0. So at mu being 5/12, there would be no acceleration. The particle would remain fixed. And that's the answer to part C.